Hey guys, this week we're doing 4.2 about energy flow, the next chapter or next section in our ecology chapter. And I'm going to defer the first part of this lecture to an expert in ecology. So I'm going to cut away just for a second to a friend of mine who's highly regarded in the scientific community, and then I'll pop back in just a second.
Everything you see exists together in a delicate balance. As king, you need to understand that balance and respect all the creatures, from the crawling ant to the leaping antelope.
But Dad, don't we eat the antelope?
Yes, Simba, but let me explain. When we die, our bodies become the grass, and the antelope eat the grass. And so, we are all connected in the great circle of life.
Yes, listen to Mufasa. You might be thinking to yourself at this point, why would I take advice from a cartoon lion from the 1990s? Well, must I remind you that he was voiced by none other than James Earl Jones, one of the finest actors in American cinema. Also, the voice of Darth Vader. That's right, Darth Vader. So, if a fatherly lion is not enough for you, consider a fatherly arch-nemesis of sorts. Anyway, moving on. Today we're talking about energy flow, the ways in which energy will flow into an ecosystem and out of an ecosystem. And as that energy flows, all the nutrition within that ecosystem must be recycled. So, to get us started, energy flows into most ecosystems in the form of light from the sun. So light enters this ecosystem, and then these producers will do a process called primary production. Primary production is defined as the amount of solar energy which gets converted into chemical energy. Again, this is carried out by our producers. Now, when this occurs, we get something called biomass. That's all the organic material in an ecosystem. So we're talking about all of the proteins, the nucleic acids, the carbohydrates, and the lipids, which have been converted from inorganic materials in the environment. This nifty little picture right above my head here, this is a map of potential primary production. Notice along the equator we have more green areas. Those green areas represent spots where there could be plenty of primary production. In South America we have the Amazon rainforest, of course. We have the Congo rainforest and its surrounding preserve and basin here in Africa. Even parts of America have rainforest-like conditions as close as the Carolinas, if you've been up that way. So the takeaway here is that if we have an excess of sunlight and water, then we can get a high primary production, which then produces plenty of biomass. Now, why does this matter? Well, the biomass produced by our producers supports the entire ecosystem because the consumers must then go in and eat that biomass. So, more biomass, more food, more living organisms, more biodiversity as it's called. So in a place where you have a considerable amount of biomass, like a rainforest, you can get an increase in biodiversity, as seen here with this shot of a typical rainforest. Notice a variety of plants seen here, rather than just the handful of organisms you might find in your yard, for example. I'm over here now. Anyway, so we're looking at a typical food chain right over here. We start with primary production. So the sun produces lots of solar energy, obviously. The plants use that energy to drive their production of food. They're photoautotrophs. So photosynthesis produces organic material, which is eaten by primary consumers. Those primary consumers are then eaten by secondary consumers, who are eaten by tertiary consumers, who are eaten by quaternary consumers, and so on and so forth. So what happens is that this biomass moves through this food chain by feeding. So the only way that this energy, this potential energy, can get through the food chain is by eating other organisms. And so as we have energy moving from one group to the next, we have a transfer of energy. Now these groups are referred to as trophic levels. Our first trophic level, we are producers. The next trophic level is the primary consumers. The next would be the secondary consumers. Each of these are called respective trophic levels. That's trophic. Now, as we move from one trophic level to the next, not all of that energy gets moved or converted. And so what happens is, let's say we're looking at this cow here. Now, this cow is going to be eating food, clearly, eating some grass, let's say. As it eats that grass, some of that grass will be broken down and then built up through anabolic reactions into cow meat or cow bones or cow muscle, cow skin, cow fur, whatever. Biomass. The cow will make this biomass. It will grow. Now, of course, not all of that food gets turned into biomass because this cow has to keep itself alive through a process called cell respiration. And so what happens is this cow conducts lots of cell respiration, and that produces a ton of heat. This is what keeps the cow warm. If you're under your blanket, the reason that the blanket warms you up is not that the blanket itself is warm, it's that your body's releasing heat, and the blanket helps to trap that heat and then keep you warm. But the point here, of course, is that not all of the food that the cow eats is converted into biomass. In fact, a lot of it is lost as heat through the process of cell respiration. Whatever does not get converted into biomass or lost as heat becomes waste, either liquid urine or solid feces, and this, of course, must be removed from the cow. This very strange setup is sometimes referred to as a cow bag or a gas bag. What we're looking at here is it's a bag with a rubber hose attached to it. And if you look closely, maybe you'll see that this hose then connects to a small incision in the side of this cow. What? Why? Why? Okay, so let's start from the beginning. Cows are ruminators, which means that they swallow their food, partially digest it, so they'll chew on some grass, they'll swallow it, it'll go into one of their stomachs. They have multiple stomachs. Then they'll regurgitate some of that food, continue chewing it. It's called a cud at this point, and they're chewing that cud, and they'll swallow it again and move on to another stomach. And so what happens is that you have a very slow, gradual breakdown of the grass that they're eating in their multiple stomachs. Animals that do this are called ruminators. And so as the food moves through their various stomachs, it produces a lot of gas. This gas mostly is methane. It's the same stuff that's in your farts or sometimes in your burps, depending on how, well, usually not, but if things are real bad. But usually that methane comes out as a fart. For cows, however, and other ruminators, that methane builds up very quickly before it gets down in the lower GI, the lower section of their gastrointestinal tract. Excuse me. So what happens is they burp out a lot of that methane. In fact, this methane is a pretty bad greenhouse gas because once it hits the atmosphere, it gets converted into CO2 as it reacts with water in the atmosphere, and so it can produce a serious greenhouse gas. It is alone a serious greenhouse gas, and then it also can decompose into CO2, which contributes to global warming or global climate change. And so one group of researchers, or several groups at this point, have been adopting these methane bags to try and capture that methane, because the methane produced from cattle ranching is actually worse in many cases than the gases produced when we drive our vehicles around. And so what they're trying to do is capture that methane and then use it as a fuel source. So it's one creative solution to the way that cattle and food production can lead to an increase in climate change. Of course, we're going to have a lot more on that. We have a whole section on climate change coming up at the end of this chapter, and we'll wrap up the whole year with the climate change project. So for now, since we're talking about cows and respiration, I thought we'd just drop this little nugget of information. Okay, now imagine that you're a cattle rancher, you're a dairy farmer, you're a cowboy, I don't know, you're a rancher, you have lots of cows to tend to. Now what you need to do is make sure that the food that you're giving this cow is converted into biomass and not lost as heat. So you want to maximize the amount of food that you're either growing or buying so that you don't waste a ton of money. So what do? Well, you try to reduce the rate of respiration in that cow. Now, you can't go in there and manipulate the chemistry of the cow to slow down their respiration. So instead, you would go in and you would cram your cows into a tighter space, and this is what's called a feedlot. And in a feedlot, you have cows, so tightly packed. In this case, this is actually a pretty friendly feedlot, relatively speaking, but they're packed in so tight that they basically can't move. Notice this white cow on the front left is covered in muck. That muck, of course, is feces, because these cows are standing in such a confined space that they have to literally wade around in their own poo. So this causes problems. So what do you do to counteract the potential for infection that goes along with walking around in your own poop? Well, you load them up with antibiotics, of course. You might give them some growth hormones to pack on some more muscle as they go along. Long story short, these feedlots reduce the movement of the cow, thereby reducing the respiration of the cow, thereby increasing the biomass. So, less movement, more meat. Enjoy your next hamburger as you think about these poor cows just standing around without movement, without joy. That's before they get slaughtered, of course. So, going back to this idea of loss of energy through trophic levels, we can look at this whole idea graphically. This little diagram over here is called a pyramid of production. What it's supposed to do is show you the amount of energy available at each trophic level. So primary production gives us, in this example, 10,000 kilocalories of energy. When we move up to the primary consumers, they convert only about 10% of that into their own biomass. And then when they are eaten by the secondary consumers, these secondary consumers only get about 10% of that energy converted to their biomass. And so we're losing, on average, about 90% of the available energy as you shift from one trophic level to the next. This is a pyramid of energy in the way that IB would like you to recognize them. It's more to scale. So these boxes should represent the actual amount or size of the available potential energy at each trophic level. Notice these boxes get significantly smaller, 90% smaller than the level below it. And that's because all of that potential energy was lost to waste or cell respiration. So this little diagram right here, this is your homework for the week, is to generate one of these. This is an energy pyramid. It needs to be done to scale, so you should show boxes which get progressively smaller, and not just randomly smaller, but 90% smaller as you move up from one trophic level to the next. You should show the correct units. That's kilojoules, that's a measure of energy, per square meter, per year. So it's energy per given area over a given amount of time. Kilojoules per square meter per year. That's the unit for these energy pyramids. You'll generate one of these. You'll, instead of just saying primary producers, you'll of course say that and then give a real named example. So if you happen to know the name of the magnolia tree in your yard, Magnolia grandiflora is the most common around here, you'd have to actually use that name for your primary producer, and then name the species that is munching on the magnolia, whatever the beetle is that might be eating it, and then name the species that is eating that beetle, and so on and so forth. So adding in named species, and then boom, you're done with your homework. Very simple. Instead of focusing on this for your homework, I want you to focus on cleaning up your notes, and then this is just our little bonus assignment. So take care of that by Friday. Before we wrap up today, I'm going to leave you with this this thought right here. I'll do this in sort of a Dora the Explorer type of question. I'll read it to you. Use the diagram to explain this quote from Mr. Lindenberg. I've decided to eat a vegan diet, plants only, for environmental reasons. And I'll pause. Can you say mochila? Good. So I hope you've considered why this option could be more environmentally friendly than this option. I won't explain it to you. I would like you to think about it yourselves. And I hope you guys have a great week. Coming back in, and I'll talk to you later.